I'm Dan Pandrungaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss second isomorphic theorem for groups from Algebra of MSc first semester first. Now see your theorem. If H is a subgroup of G, N is a normal subgroup of group G, then H n divide n is isomorphic to H divided by H intersection n. For proof, it is clear that H is a subgroup of G and n is a normal subgroup of G. Therefore, n is a subgroup of NH and n is a normal subgroup of G. Therefore, n is a normal subgroup of Hn. Hence, Hn divided by n is defined. Now H intersection n is normal subgroup of H. Therefore, H divided by H intersection n is defined. Define mapping from Hn to H intersection H by H intersection n by phi of Hm is equal to H intersection n into H. Now claim that phi is well defined. For well defined, suppose that h1 n1 is equal to h2 n2 for h1 h2 belongs to h and n1 n2 belongs to n. Therefore h1 n1 is equal to h2 n2. Therefore h2 inverse h1 is equal to n2 n1 inverse, and n2 h2 inverse h1 belongs to h. N2 N1 inverse belongs to N. Hence, S2 inverse H1 is equal to N2 N1 inverse. Therefore, S2 inverse H1 belongs to H intersection N. Therefore, H intersection N into H1 is equal to H intersection N into S2. Therefore, phi of H1 N1 is equal to phi of H2 N2. This shows that phi is well defined. Now we have to prove that pi is a homomorphism. Phi of h1 n1 h2 n2 h1 h2 belongs to h, n1 n2 belongs to n. Phi of h1 n1 h2 n2. N is a normal subgroup of G and Hn is equal to nh. Phi of is equal to phi of h1 s2 n3 n2 phi of h1 s2 n2 n3 n2. Therefore, H intersection n into h1 s2, that is H intersection n h1 into H intersection n s2. Therefore, phi of h1 n1 is equal to phi of s2 n2. This shows that phi is a homomorphism. Now we have to prove that phi is onto. Let H intersection n into H belongs to H divided by H intersection n. Then H belongs to H. As H belongs to H, H belongs to Hn, and phi of H is equal to phi H intersection n H. This shows that phi is onto. Therefore, pi is 1 1, pi is well defined, and pi is a homomorphism. Therefore, pi is a isomorphism. Therefore, Hn divided by kernel pi is isomorphic to H intersection H divided by H intersection n. Now we have to prove that n is a kernel pi. Kernel pi is equal to Hn belongs to Hn. Pi of Hn such that pi of Hn is equal to H intersection n is equal to Hn belongs to Hn, so that H intersection n H is equal to H intersection n is equal to Hn belongs to Nh, such that H belongs to H intersection n is equal to n. Therefore, kernel pi is equal to n. This shows that Hn divided by n is isomorphic to H divided by H intersection n. Third isomorphic theorem. Let H and K be normal subgroup of a group G with K is a subgroup of G. Then G by H is isomorphic to G by K divided by H by K. Let H and K are normal in G and K is a subgroup of G, subgroup of H. Then K is a normal subgroup of H. Thus G by H, G by K, H by K are all defined. Now define a mapping phi from G to G by K divided by H by K by phi of G is equal to H by K into Kg for all G belongs to G. Now claim that phi is well defined. Let G1 G2 in G, G1 is equal to G2 in G, therefore G1 is equal to G2, Kg1 is equal to Kg2, H by K, Kg1 is equal to H by K, Kg2, therefore phi of G1 is equal to phi of G2 and hence phi is well defined. Now we have to prove that phi is a homomorphism. Let G1 G2 belongs to G, phi of G1 G2 is equal to H by K, K G1 G2 is equal to H by K into Kg1 into Kg2, H by K into Kg1 multiply H by K into Kg2, therefore phi of G1 into phi of G2, that is phi of G1 G2 is equal to phi of G1 into phi of G2. This shows that phi is a homomorphism. Now we have to prove that phi is onto. Let H by K into Kg, Ka belongs to G by K by H by K. Then A belongs to G. For this, A belongs to G. Phi of A is equal to H by K into Ka. Therefore, phi is onto. As phi is well defined, phi is onto, phi is a homomorphism. Therefore, by first isomorphism theorem, G by kernel phi is isomorphic to G by K upon H by K. Now we have to prove that kernel phi is a subgroup H is itself. Kernel phi is equal to x belongs to G such that phi of x is equal to H by K. X belongs to G such that H by K Kg Kx is equal to H by K. Kx belongs to G such that Kx belongs to H by K is equal to x belongs to G such that x belongs to G, therefore kernel phi is equal to H. Therefore kernel phi is equal to H. Replace in G by kernel phi isomorphic to G by K divided by H by K. Therefore G by H is equal isomorphic to G by K divided by H by K. Thus lemma. Let H and K be subgroup of G, S star and K star be the normal subgroup of G, H and K respectively. Then prove that S star H intersection K star is a normal subgroup of S star H intersection K and K star H intersection S star intersection K is a normal subgroup of K star into H intersection K. And S star into H intersection K divided by S star H intersection K star is isomorphic to K star S intersection K divided by K star S star intersection K is isomorphic to H intersection K divided by S star intersection K into K star intersection H. Now proof we have to given it is given that H intersection K is the subgroup of H, therefore S star is a subgroup of G, normal subgroup of H. Therefore S star multiply H intersection K is a subgroup of H. Now H intersection K is a subgroup of K, therefore K star is a subgroup normal subgroup of K. This implies that K star H intersection K is a subgroup of K. Now S star intersection K is a normal subgroup of H and S star intersection K is a subgroup of K. Hence S star intersection K is a subgroup of a normal subgroup of H intersection K, and similarly K star intersection H is a normal subgroup of H intersection K. Hence S star intersection K into K star intersection H is a normal subgroup of H intersection K, and this further shows that H intersection K divided by H star intersection K into K star intersection H is well defined, which define. Now put L is equal to H star intersection K into K star intersection H. Thus, L is a normal subgroup of H intersection K. Define a mapping phi from H star into H intersection K to H intersection K divided by H star intersection K multiply K star intersection H by phi of Hx is equal to Lx, that is H star intersection K into K star intersection Hx. Here H belongs to H star and X belongs to H intersection K. As phi is well defined, we have to prove that phi is well defined, and so on. H1 x1 is equal to h2 x2. For h1 h2 belongs to H star and x belongs to H intersection K. H2 inverse h1 is equal to x2 x1 inverse. For h2 inverse h1 belongs to H star and x2 x1 inverse belongs to H intersection K. Therefore h1 h2 inverse h1 belongs to H star intersection H intersection K, and this shows that h2 inverse h1 belongs to L, that is H star intersection K into K star intersection H, and x1 x2 x1 inverse belongs to L. Therefore Lx1 is equal to Lx2. Therefore pi of h1 x1 is equal to pi of h2 x2. Therefore this shows that pi is well defined mapping. Now we have to prove that phi is homomorphism. Let h1 x1 h2 x2 belongs to H star H intersection K. For h1 h2 belongs to H star and x1 x2 belongs to H intersection K. As H star is a normal subgroup of H and x1 belongs to H, we get x1 H star is equal to H star x1. Therefore x1 h1 h2 belongs to x1 H inverse. This implies that x1 h2 belongs to H star x1. Hence x1 x2 h2 is equal to h3 x1 for some h3 belongs to H star. Hence we get phi of h1 x1 is equal to h2 x2 is equal to phi of h1 x1 h2 x2 is equal to phi of h1 h3 x1 x2 is equal to phi of h1 h3 x1 x2 is equal to lx1 x2 is equal to lx1 into lx2 is equal to pi of h1 x1 into pi of h2 x2. Therefore pi is a homomorphism. Now we have to prove that pi is onto. Therefore let Lx belongs to uh, H intersection K by L, then X belongs to H intersection K. Hence E star X is, belongs to H star intersection S star into H intersection K, and pi of Ex is equal to Lx. This shows that pi is onto. As pi is well defined, pi is homomorphism and pi is as onto. Therefore by second image of by post isomorphism theorem, H intersection K divided by L is equal to isomorphic to H star into H intersection K divided by kernel pi. Now we have to prove that H star K kernel pi is equal to H star into H intersection K star. Now kernel phi is equal to hx belongs to H star into H intersection K, such that phi of hx is equal to L. Hx belongs to H star into H intersection K, such that Lx is equal to L. Yeah, therefore hx belongs to H star intersection into H intersection K, such that x belongs to L, and hx such that h belongs to H star and x belongs to H intersection K intersection L, and Hx such that H belongs to H star and X belongs to L, nothing but H star intersection K into K star intersection H. Therefore, Hx such that Hx belongs to S star into L, and such that Hx belongs to S star into H intersection K star and is equal to S star into H intersection K star, and hence H intersection K divided by L is isomorphic to H star into H intersection K divided by H star into H intersection K star. Kernel phi being a normal subgroup of S star into H intersection K star, we get S star into H intersection K star is also a normal subgroup of S star into K H intersection K, and therefore H intersection K divided by L is isomorphic to K star into H intersection K divided by K star into H star intersection K, and therefore K star into H star intersection K star is a normal subgroup of K star into H intersection K, and this is the lemma's proof of this lemma, and we complete the our today's task.